We have two more reactions left on this worksheet. Let's start by highlighting the carbons in the reactant that are also present in the product. So we can see that we're going to need to add some carbons to this molecule. We're going to need to add quite a few carbons to this molecule. I do notice that we have an enamine. And we only know one way to make enamines. So what I'd like to do with this molecule is start at the enamine and work backwards and see if we can get all the way back to benzene. So with our enamine, retrosynthesis is kind of tricky. Remember, what we want to do is start by visualizing the double bond in between the carbon and the nitrogen. That'll make it easier for us to figure out how this molecule breaks apart. Once we can see that, we know that the carbon-nitrogen double bond is what used to be a carbon-oxygen double bond, like that, and our other piece, the nitrogen with two methyl groups on it, has a hydrogen added to it. This is going to get put on the ketone with acid catalyst, so there's those reagents. And now let's think about how could we make this molecule that we just made, the ketone, how could we make that from benzene? And that's actually pretty simple. This was one of the reactions that we learned at the end of 242. This would be a Friedel-Crafts acylation reaction. It'll allow us to make the ketone right onto the benzene ring. Don't forget the AlCl catalyst, so that's not too bad. This last one down here, though, is super scary to me. I don't like the way this one looks at all. Let's start by finding our carbons. So we can see we've got these two methyl groups, and there they are right there in the product. And the carbons that are attached to them, they're right there. And then they have two more carbons attached to them, so that's these parts right there. So there's the original carbon skeleton that we're starting with. And that means that this stuff down here is the stuff that we need to add. And that's an acetal, which we know how to add acetals. So we're going to work this problem backwards, at least initially. With the acetal, remember, we're going to focus on the OCO. We're going to pick either one of those carbon-oxygen single bonds, and we're going to turn that into a carbonyl group. We're going to break the other carbon-oxygen single bond and break the oxygen off of the molecule. So let's see what we've got. We have, first I'm drawing the carbon skeleton in yellow, and it has a bond to an oxygen, and then it has this bond that we broke. And we also have the carbonyl group down here that looks like it's just going to have two hydrogens on it. To the other part, not the aldehyde, but the other part of the molecule, we need to add an OH and an H. And this is going to be acid catalyzed, so we'll put that in there. So we've got that much of it figured out, and I'm going to highlight our carbon skeleton again. So now we need to figure out how to turn this weird diene into this diol molecule. Let's find the carbons that we want to focus on. These carbons in red, these are the ones that we want to put OH groups on. Now, I don't want to put an OH group straight onto an alkyne. We can kind of do that, and then it's going to want to do some enol tautomerization, which we can work around it, but I feel like there's probably an easier way to do this. I feel like it would be easier for us if we were adding OH groups to alkenes, to a diene, instead of adding OH groups to alkynes. And this is not a conjugated diene that I just drew, so we don't have to worry about any of those like weird addition to conjugated diene, rearrangement, thermodynamic, kinetics, all that kind of stuff. We can just do a regular, normal addition of water to an alkene. if we could figure out how to make an alkene. So let's put some reagents down for this. I can see that we want this to be a Markovnikov addition, and I don't want the possibility of anything rearranging and screwing up that carbon chain. So we are going to use oxymercuration demercuration. HgOAc2 with water. That's our step 1. And step 2, sodium boryl hydride. So that'll put the OH groups in the right spot, and we don't have to worry about a rearrangement. And now all that we need to do is figure out how to convert that alkyne into the alkene. And we can do that with either one of our single step hydrogenation reactions for the alkene. So that would be the reactions that we would use to make a cis alkene or a trans alkene, except for in this case they're terminal alkene, so it doesn't matter. So probably on paper the easiest one to do would be H2 with Lindlar's catalyst. And it turned out that problem wasn't that bad after all. I'm going to highlight my carbon chain, and we did it.